Well, hi, welcome to day 2. I hope that you had a chance to look over what we did yesterday. I'm going to treat things like the assignment operator as a given, that we understand how that works. Today we're going to be working a lot more with something called data frames, which was a concept that we looked at the very end. What were the data types that we discussed? You remember the first one was vector. Everyone remembers vector. So a vector is a data type that means that you have a series of things that are the same type. So if you started with numerics, they're all numerics. You could also do a vector of things like character strings, though. If any of them are characters, all of them are treated as characters. You could also do vectors of Booleans, for that matter. So we then moved into doing that in 2 dimensions. You remember the matrices with columns and rows? In many, many respects, matrices are just like vectors in 2 dimensions. They have to have all the same type of data type. So if you have a numeric in the upper left corner, the bottom right corner is going to be a numeric as well. Data frames, as you probably recall, are a little different than that. In effect, a data frame is like a list. Do you remember we demonstrated a list as by the example of the list that t-test gives us back. It has elements in it like the p-value, it has elements like the t-statistic. Well, data frames are also a list, but they're a specialized kind of list. Each of the items in a data frame list is a vector of the same length. So if you have a data frame that has a field with name on it, then and you have 26 items in that vector, then you're required to have 26 items in all the other vectors, but the other vectors are not required to be characters. They could be numerics. So we're going to create examples of that today and write them to disk and read them from disk, stuff like that. Okay, so I'm going to start with a table of quiz scores that we're going to simulate here. So I went to a baby naming website for people who speak I can't click it. I'm sorry. My tongue is not behaving itself today, so we'll leave that alone. But I thought it would be useful to borrow some names from that language. So we have Bongani, Lendelwa, Temba, Dumisa, Tandiwe, Olwetu, and Kwesi. Did I do okay? Oh, thanks. I appreciate that. Now, are any of those names completely out of use and we should never have included that? I know at least one Temba. So a couple Bonganis, I think. So, all right. So we're going to create a vector of names, and then we're going to have a model for how solid a student each person is. These are just randomly assigned. So I'm going to start with just those 2 lines and copy that into R. Oh, before I move off of the screen, there's a story that's too good to tell here. Most programmers express their senses of humor in how they name their software. Okay, so if you look at the very top line that you see on screen, you see that I'm using a very old version of R from 2 years ago. That's very embarrassing. Version 3.4.0, and it is titled, You Stupid Darkness. Yes, it's called You Stupid Darkness. This comes from an old expression saying, it is better to light a candle than to curse the darkness. So this version of R is cursing the darkness. You stupid darkness. Programmers are just like this, I'm afraid. So anywhere you go looking, you're going to find examples of programmers naming things creatively. To use a very long-standing example, we have the name Apache Web Server. Now, a web server is software you install on a computer so that if somebody tries to contact it via a web browser, it responds with web pages. And Apache was, for a long time, the dominant web server that you could install on your computers. But most people don't know where its name comes from. It comes from the fact that they had borrowed code from a web server produced by someone called NCSA. And over time, they found a whole bunch of different things that they wanted to add as features to the software. And those little differences between what they wanted to add and what the original version of the software are called patches. So a patch reflects something you want to change about the source code to make it do something you want it to do. So over time, they decided that rather than storing their version of the web server as a series of patches, they would release their own version of the software and just call it its own thing. And so they called it Apache Web Server. Now, Apache is an Indian tribe in the American Southwest, Native American tribe in the Southwest of America. But it also sounds like what the server started out as, a bunch of patches. You find this stuff everywhere, so I'm just telling you to keep your eyes open, and you'll catch all sorts of little jokes on their way. All right. Now I was copying a couple of lines from this code. We're going to create a vector of names and a vector of averages. Well, I've just botched something here. What did I do? Oh, I'm sorry. I didn't copy this first. I needed to do that. Sorry. Okay. Great. So now we have a vector of names. We have 7 names. Everyone sees that, I think. And we have a bunch of averages. So in this case, what's our high score? I could find out which is our high score by saying max averages, but here sort was easier. So I can see that the worst average we're going to see is 69.6%, and the high is going to be 92%. So these are just scores that are going to help guide how each student performs on the quizzes. All right, and now I'm going to build a matrix with 7 rows, each one corresponding to a different student, and 10 columns. And it's going to have a vector of names that's going to have quiz 1, quiz 2, up through quiz 10. And we're going to add in some quiz scores that are going to be simulated for each student based on what their averages were. Okay. How I do all of that is not strictly speaking necessary to know, but I would just try to flesh this out a little bit. So we had 7 names, therefore 7 rows. We're going to have 10 quizzes, thus 10 columns. You can see that I've provided the names as the row headers, and then I've provided the names of quizzes for the column headers. All very straightforward. But then we had to write something into this. You know, if I just look at what the quiz scores looks like after I create it, it's not very interesting. So I can grab this. Okay, so what does quiz scores look like at this point? We've got more Batman. No. But we're now going to write in a whole bunch of values. Now I'm cheating because I'm using a for loop, and we're not going to discuss those until tomorrow. But what I would like you to see is that it's going to replace each row of quiz scores, that it starts out as a bunch of not applicables, and it's going to fill numbers in that have been randomly sampled from what's called a Poisson distribution. Okay, so having done that, quiz scores changes from this grid of NA values to a grid of scores instead. I had it loop through each student and write in a bunch of quiz scores. So your quiz scores object should look like that. Anyone that doesn't get that result? So in effect, we started up here, and we've now run all the way through this for loop, and that gave us the quiz scores matrix. Okay, now we're going to write that table to disk, and this is the command to do this, and I want to try to walk through several pieces of this. We're going to be interacting with files in a variety of ways today. To start, we're going to create a text file that represents the contents of quiz scores. But it needs some information on how to do that. So we've got a series of variables we're feeding it. One is quiz scores itself. So we just looked at what that matrix looks like. The matrix does not have a field called names. It doesn't have a field called names. What it has is rows that have been labeled with names. There's a subtle difference there. It's just one you should be aware of. Secondly, the columns are named Q1 through Q10, but in the software, they're just columns 1 through 10 with these names applied to them. There is no row you could pull out that contains the quiz names. All right. So we're going to feed it quiz scores as the object we want to write as a table to disk. We have to tell it what file we want to create in doing so. And since we're creating a text file, one of the obvious things to do would be to call this quizscores.txt, but I didn't use that option. Instead, I used TSV. You will frequently see files with a name TSV and CSV if you do any amount of bioinformatics. TSV means tab-separated values, meaning that we're separating the different fields of the file with tab characters. We sometimes use commas to delimit these lines. Delimiting means to add in a character that always says this is the start of a new field. So tab delimiting and comma delimiting are the two most common ways that we do this. And corresponding to that, we need to specify a symbol that it's going to use to separate fields from each other. Here we've used tab. \T means tab in this case. So let us now run this and see what results. Okay, so it didn't give us any feedback, it just did it. And one of the things that we can do is check our current directory to make sure it wrote something called that. And here I see that number 25 on my list is called quizscores.tsv. That's great. So, right. So quiz scores. So this is what the object I'm showing on screen right now is what it has in memory. But I'd like to see what that file looks like. So I'm going to open my favorite text editor, which is Emacs, and I'm going to try to navigate to where this is. Actually, it's going to be a little challenging to get there. This is going to be in, it's not going to be in the directory where we're storing all this stuff. It's going to be in documents in my case. So if I go to quiz scores TSV right here, I can open that in a text editor pretty easily. Hello, text editor. You could do this in Notepad, that would work. All right, if I just drag this over, I see that this is what I've captured in my text file. So you see how all of these columns line up with each other? Those columns are lining up with each other because we use tab to space them out. Nothing too remarkable there. One of the other nice features about tab-separated files is that generally you can move them into Excel quite easily. So if I open Excel, oh, sorry, I'm mistyping, Excel, here we are. Just start that up. I'm now going to just drag that over to Excel. Let me get that out of the way. Okay, there's my Excel window. I'm now going to drag our quiz scores thing over to Excel. And it may just open correctly. That would be lovely. Look at that. Okay, so Excel knows to look for tab characters as a likely delimiter, and we see that information is there. But what happened at the top? This is one of the oddities of how R tends to write its data files out. It doesn't write in a header that corresponds to all the names. So in this case, to make these line up properly, I would need to grab these cells for the headers and scoot them all one to the right, and now they're over their correct columns. It's a relatively minor change to adapt between an Excel import of the file and the file the object that we had. Okay, I'm going to close this again. Close that nonsense. Close this nonsense. Okay, we come back here. So what we had in memory was a particular data type. Remember that we created this as a matrix. And if I come here, I can use the class function to tell me what kind of object that is. What is the data type? And remember, it's a matrix. So the characteristic of a matrix is that it has a certain number of columns and a certain number of rows, and it has the same data type in each. In this case, a numeric. All right. Now we're going to, there's my direction. I was supposed to import that into Excel, so we're already ahead of ourselves. This time, though, we're going to read the file that we've created back into a variable in memory. So it exists as a file now. We're going to load that back in because something is going to change that's kind of important when we do that. Okay, so we had a variable called quiz scores. That's what we wrote. When we read it back from disk, this time we called it quizzes. So what changed in the process of writing and reading that file? Suddenly, our matrix is no longer a matrix. The default behavior for read table is to create a data frame from the file that we read from disk. So if you remember, we used the transpose function on a matrix yesterday, so we could say quiz scores transpose. You see now all of the columns have become rows and the rows have become columns. Can we do that same operation on the object we just read from disk? We can. That's nice. Okay, so transpose is going to work with the data frames just as well as it did with the matrix. That's a very helpful feature. Okay. Right, so we're now going to ask which quiz gave the students the most trouble. This is always the question I end up asking after I do my bioinformatics teaching across the way. You know, sometimes I'm just in a really mean mood when I write a quiz and the questions are harder, and sometimes I'm in a better mood and the students got everything and they just aced them. So I want to know which quiz gave the students the most trouble. All right. So I see that I got back a little more than I can show on screen all at once because I'm doing big screen, but we see that for quiz 1, our mean score was 33. For quiz 2, it was 34. Quiz 3, 32. Not a lot of variation here. And one of the reasons for this is that these data were simulated, and I didn't tell it to make any of the quizzes harder than any of the others. So the scores are not really changing as a function of which quiz it is. All right. Now, we had a set of averages that we used to inform the computer how well each student was going to perform, and it created random samples of quiz scores to figure out how they did. Let us ask if the quiz averages that resulted from those simulations are just like what we had. So we're now using a function called row means. Row means is a way to parallelize this process. Remember, we have our quizzes object. Row means is going to compute an average for each row, one after the other. So row means is giving us an average for Bongani, an average for Dumisa, etc. So I could put these together with something like data frame names and quiz averages. This is one way to get all the names associated with particular averages. And you can see that in this case, Bongani averaged 28.8, Dumisa averaged 33.1, and so on. So row means is a very rapid way to do these averages all up and down the set of rows that we have. Okay. In this case, I thought it would be useful for us to stick those averages onto the table that we had the quizzes themselves in. This is the sort of thing you would do in Excel all the time, right? You've got your original data points, and now you're adding a new column called mean, and you just write that right into the table. The equivalent of doing that in R is going to create that column, the row means call up here, and then it's going to bind it to the table that was already there. So cbind is a column bind. You remember yesterday we used an rbind to add a new row onto a matrix. Cbind is the opposite. It's going to add a new column to something that already has a bunch of them. So I've called that quizzes plus averages, and when I play that back, I see that the quiz averages have been added. Now there's kind of a subtle difference between all of those Q columns and this new one, the quiz averages, right? The software remembers that the quiz scores are all integers, so it's not showing me 0.0 on all of those. But quiz averages is being treated differently. It's being treated as a floating point number, so it gives us the first decimal point after the for each of these values. All right. Let's see. Did we get a separate column for the names of people? That was the other thing I wanted to ask. So I'm going to run the summary on quizzes plus averages. Remember, summary is my go-to command for almost everything. And I ask what came back for this. Okay, so quizzes plus averages did not get a name column when we read this back in. It understood to interpret those as the labels for each row. There's another command I should show you here as well. I'm going to just repeat the last command by hitting the up arrow key. And now I'm going to say dim of quizzes plus averages. This is the dimensionality of the data. So we have 7 rows and we have 11 columns. Remember, when in matrices or in data frames, you're always going to see the row information first, then column. We sometimes think, okay, when we're giving the coordinates of a point, we'll give the x first and then the y. R is going to reverse that, though. It's always going to give us the row number first, then the columns. Okay. So we used the index operator yesterday with vectors. As you recall, we went looking for the second item in a vector. So we just said that vector's name square brackets around a 2, which grabbed back the second one. That also works here, but because a vector, or a data frame in this case, is a 2-dimensional entity, we have to provide both of those. So let's now create a subset of the data using the index operator. So here we've specified, because we know Bongani was the first student in this table, that we're going to grab the first row. But you see, I didn't specify, give me row 1, column 2 through whatever. I just said, give me row 1, comma, nothing. And in R, that means give me all of it. So if I say quizzes bracket 1, comma, and then nothing after that, it means give me the whole first row. So when we list out Bongani row, we see it still has his name associated with it. That name attribute hasn't gone away. And we have all 10 of those values from quizzes. Now you can specify that other information. Let's say you wanted number 5 from that. See, now Bongani row is not giving us the whole row, it's just giving that one cell. And quiz 5 was the 30. We see that that's now been copied into Bongani row. But I'm going to change this back to what I had earlier. I'm just going to grab out the whole first row for him. Or her. Sorry, I've met Bonganis who are males and females, so okay, so I don't mean to be to insist it should be a male name. All right. I can also do something like which quiz gave Bongani the hardest time and the best time. So if I grab that, I can sort the whole row, and now the software remembers which label goes with which score. Isn't that handy? So even though I've sorted it, I've rearranged all these quizzes. It's no longer listed quiz 1 to quiz 10. It's listed quiz 7 to quiz 9 because it's changed the sort order from the original column order to the order of the score. Okay, so that's all I really wanted to do with the quizzes in particular. Are there any questions that this part causes you? Okay. Right, so we're now going to use something that looks a little bit more like the data we would use in a biostatistical analysis. So we're going to use the names again. We're going to add a column for sex, for height. I think that was height in centimeters, weight in kilograms. And I'm going to add some blood pressure. And then I'm going to write it all into a big data frame called vitals. So I'm going to just run this whole block of code. All right, so individually, these are just what you would expect. We've got a bunch of heights, got a bunch of weights, a bunch of systolic. Anyone remember what systolic and diastolic are all about? One of my favorite terms in medical terminology is the blood pressure cuff. Does anyone know what the technical name for that is? It's like the sphygmanometer. It's an amazing name. All right, that's useful for producing systolic and diastolic blood pressures. Okay, so when I enter vitals, weights wasn't here. Oh, weight was there, but weights wasn't. Okay. This is more typical of what we expect from a data frame because we have different fields that each have names and they're different types compounded together. This is not a matrix. No one should be confused that this is a matrix because it has the fields of names and sex in there that wouldn't be allowable in a matrix of numbers. Okay. What else did I want to say about this right now? Well, I think I wanted to talk a little bit about, okay, yeah. I wanted to I wanted to note that R has done some useful things for us along the way. These started as vectors, right? And they were vectors of the same length, which was critical. All of these are 7 elements long. We have 7 systolic blood pressures, 7 diastolic blood pressures. We have 7 weights, 7 heights, 7 sexes, 7 names. That was required in order to make a data frame. The other thing that the software has done, though, is to remember the name of the original vector that was fed into that. You see that it has remembered that these numbers were all in a vector called systolic, and it's preserved that when we stitched it all together to make this data frame. So that's a pretty handy kind of trait. Yesterday we talked about factors. Do you remember that? So if we were to do a class vitals weight, we see that that's still numeric. But if we look at class vitals sex, we see that it's a factor. Now, did we tell it that was a factor? If we look back at our code, we see that sex was just a string of, just a vector of character strings, right? A bunch of F's and M's. But data frames, as you create them, will assume that these strings are to be interpreted as factors. And that's kind of a weird behavior. In some cases, that can really mess you up. Did it do the same on names as well? It did. So this is kind of an odd behavior. Imagine that you had a couple hundred people that you were writing into this table. Is it important that the software note that there are multiple people named Wongani? Not so much. And yet that's what factors do. It notices all the distinct names that are there and looks for duplication of them. So there are ways that you could create this where it would remember that those are characters and not factors. But in this case, it doesn't matter a huge amount. All right, so we now have our vitals here. Let's write them to disk the same way that we did before. Is it clear how I would change this to use commas instead of tabs as delimiters? I would change 2 things. I would change my file name extension from TSV to CSV to reflect its commas, and I would need to change the separating character to comma rather than tabs. Okay, so I'm going to write that table off. Now I have a file called vitals.tsv on my hard drive. Okay. So here I've got my comment to myself that I'm supposed to talk about these vectors as factors and vectors of characters. It's something we've already done. Okay, so it is also possible then to read these tables back into memory as a new variable name and so on. It's just useful to be able to do that. But sometimes you would like to store these things not as text files, right? Text files are pretty good. If you're communicating to outside software, that's really a friendly way to do it. To be able to write a TSV files will be handleable if you use Excel or Quattro Pro or whatever software out there you're using to read this back in. That's not going to be a problem. Does anyone here use GraphPad Prism, for example? If you had to swap off information between this and GraphPad Prism, passing around information as a TSV is a pretty easy way to do it. Sometimes, though, you know that you're going to come back to this in R itself. And for something like that, it's actually quite valuable if you can create an R object file. So I can specify that this object, vitals, is something that I want to reopen later in R. So if I grab this line, I can do that. So vitals was this. You can see that I might want to just, maybe I've overwritten it subsequently. Now vitals has been replaced with nothing. I need to now recreate the vitals object as it was when I saved it. So I can specify to just reload that from disk. If I open it, I see that it's back. Now what was really odd about that load line? Did I tell it what to capture the output of loading that file from disk? I did not. So this is one of the limitations of writing an object in this way. when I do that, in this case I've called it vitals.rdata, but I could have called it anything.rdata. When I reload that, it's going to recreate exactly the same names as those objects that were saved. So it's kind of an odd default behavior for these things. Okay. So for the other part of this show, I wanted to demonstrate the reading of an Excel spreadsheet. So this morning I added an Excel spreadsheet to the web directory for this. That is back one file, I think, but no, here I'm opening it from disk. I don't have it in front of me, but I have copied this this Excel file right here. I'm gonna just go ahead and open it so we can see what we're looking at. All right. So an Excel superficially, an Excel file looks an awful lot like a data frame, doesn't it? And at least in the way I've structured this one. You see that I have a numeric field here with a name header. I've got a bunch of silly names here. These are character strings. And here I've got some prices. These are, again, just going to be integers. But if you look a little more closely, you'll notice that Excel has other features like multiple worksheets. So when we deal with Excel data, it is possible to write out a tab-separated values file from here. Does everyone know how to do that? Well, I think we're all accustomed to the Save menu. Save As is a special option, though. You see that by default, we're going to create an XLSX file when we save from Excel, but we also have the ability to write a CSV file, the comma delimited, and I believe in here, yes, we also have tab delimited files. Now it's a little bit of a misnomer because it creates a file with the extension txt, but it's actually tab delimited, so it's not a TSV file, except that it is. It's just not called one. So it is possible to write a particular worksheet out as a TSV or a CSV using Excel. That is the easy way, typically, to just export data to R. But on occasion, you want to work with an Excel spreadsheet as it is. If, for example, you wanted to record everything that you did to alter data, to alter the formatting of data en route to an analysis in R, and your collaborator has given you an Excel file as a starting point, it's probably worthwhile to be able to note all the things that changed as you analyze those data points. So in that case, you may not want to export this as a text file before you work with it in R. Okay, so we have the option of reading data directly from an Excel file, but this step is going to require network connection, so this may or may not work for you in here. We'll just try our best. So I'm going to install a package. There is a tremendous taxonomy of different packages that have been made available for working in R. If you want to make Venn diagrams, there's a package for that. If you want to read RNA-seq data, there's a package for that. It's an incredible array of them. In this case, we're just using the readxl library because that's the one that will enable us to read this particular file. In my case, it's going to ask me where I want to install it from. There are a huge number of options. It is always good practice to try to use a mirror that's close to you. I should explain that a mirror, in this case, there's not just one place you can get R packages. The Comprehensive R Archive Network, or CRAN, has servers all over the world. Now, as you look through this list, you might say to yourself, my goodness, I'm sure there's one for South Africa, but wait, it's missing. In fact, we do have Comprehensive R Archive Network archives here in South Africa, but they're listed under other mirrors. That's because they're not secure servers, they're just open servers. So if we go through the other CRAN mirrors, suddenly South Africa appears just fine. We have a Cape Town one and a Johannesburg one. So what does that tell you about Durban? That's right, they're just not as good as we are. All right, so we're gonna pick Cape Town. All right. It's working for me at least. I installed this earlier so it doesn't have to redo it. It should download it and install it and everything should be fine. Okay. Did that work for other folks or was it bulking on the network? It's working. Oh, that's lovely. Okay. It is not enough to have installed the library. We must also tell it we intend to use functions from this library. So you'll see that I've listed not just install packages, but also the library function itself from that. The library function is used to say, we are now going to use functions from the readxl library. So if I come over here and paste that in, it gives me a little warning here. It might be a little unnerving to receive this if you're not accustomed to computer software. One of the things that programmers have learned over time is that it's best to say something about a potential mismatch in the software. In this case, I am using a version of R that's numbered 3.4.0, I believe. 3.4.0 is what I'm using. It's old, very old. But you'll see that readxl was not compiled for version 3.4.0, but rather 3.4.4 in my case. Is this going to cause a problem? Not in the least. Most of these warning messages are warnings and they're there to let you know, but generally speaking, if you see a minor version mismatch like this, you wouldn't worry too much. If that warning message said that the library was compiled for version 3 and I was using version 4, I would probably be more worried about it. In this case, we only have a 004 difference between the version it was built for and the version I'm using. It's very unlikely that's going to cause a problem. Okay, so now I've run the library command to specify I'm going to use this. If you were using a script, you might put in a more forceful command like require. If you use that in a script, it's going to throw a pretty big message if somebody has not installed this library in the past. So something like that is also feasible. All right. Now, I have a note here, and I probably should have put it in all caps. If you are not in the directory that contains your spreadsheet, this is not going to work. So I need to change this directory to go to the place that actually contains that sheet. And unfortunately on my computer that's going to be buried under a few layers of stuff. So we're going to get there. I come to the File menu which says Change Directory. This is one of those places where if you're using RStudio, you might end up with a somewhat different result. It is possible in RStudio, I think, to just drag the spreadsheet to the current working directory, but rather than changing R to go look at the directory where it is. But I'm going to go ahead and just change this over to that place because that's, oops, sorry, I don't need my photography record here. All right, own cloud, documents, archives, Sun, courses that are taught, and then I want my 2019 UWC stuff. There we go. This is the directory it's in, so I'm just going to say OK. I can run list files to see what's in this current directory. Ah, we're in the right place. See, my Excel sheet is right here, inventory. Okay, now I am going to try the readxl command, but remember, when I looked inside that Excel sheet, I had two different worksheets within it. So I need to specify which one I want to read. In this case, I'm going to open that Excel file, and I'm going to grab the inventory sheet from it. So it's okay for programmers to complain about other people's code, right? So here we see that the readxl library is making use of another library called table. And so both of these packages have to be in place for the software to work. And it's complaining that my table is old. I'm really sorry. I'm just not going to change that. So that's fine. And now I'm going to grab out prices separately. All right. So inventory looks like this, and prices looks like that. So If you remember from the Excel document, each of those represented different worksheets. I don't have to switch between them. I just need to tell the software which one I want to grab information from. You know, in Excel, when you're clicking around on all these different tabs, it's easy to get lost sometimes. So you can only have just the one open to your view at one point in time. In R, you can grab out that information, store them in different variables, and then you have it. Now, there are some, to very much underestimate the case, I would just say there are some differences between tables and the data structures we've grown accustomed to. Remember, we've seen matrices that looked an awful lot like these grids, but we've been working today with data frames. But in this case, we've created a table. Tables come from a completely different implementation of data tables that are associated, if I recall correctly, with the tidyverse libraries. In this case, it doesn't make a huge difference. I can still say, for example, inventory row 3 and get back that information. But it does have some differences with what you'd expect in a data table. A data frame, rather. Okay, so that's the demonstration that I have for today. You asked a lot of good questions yesterday, and today you're sitting more silently. I haven't stopped to say, does everyone get that? Could you give me some questions? But I hope that this exercise of reading and writing files that are text makes sense, that you can, if you've put together an analysis in R, you have a way to export that information. That if you have created a table in Excel, you have some idea of how you'd go about exporting that information into R. You'd write it as a TSV and then read it. I hope that you have some notion of how to save an object that you've created in R to a file and to reread that from the disk as well. And that you have some notions on how you would go about grabbing data out of an Excel spreadsheet, because this is biology and a lot of people are passing around valuable data on spreadsheets. I will try to save for another day why Excel spreadsheets are really problematic for storing a lot of biological data, especially gene names. There's a gene family called the septins that if you use those labels in an Excel spreadsheet and try to you read it into a spreadsheet, it will suddenly turn all of the septin family gene names into dates for you. There are a lot of horrible things that really should stand in the way of using Excel a lot for molecular biology work, but this is something just to be aware of. Today, you learned how to get data in and out of R, and I'm really grateful for that. So if there are no more questions, not even hiding in the back corner, no questions back there? Not a one? Okay. You're not trying to get away from our programming by sitting back there, are you? Okay, that's good. All right. Great. Programming has people who love it, and there are people who hate it. And sometimes it's the same person on the same day. It's true. If I'm having a programming day, you'll probably see me jumping up and down and stamping and shaking my head. And then a moment later, you'll see me in my great victory sign. You know, programming is absolutely fantastic for making you feel like the smartest person on earth one moment and the absolute dumbest brick the next. So, you know, I've carefully canned what this script looks like and what we're going to do in class, and I've tried to guide us down a line of things that I know will work. And I know what will work because I've tried 1,000 things that didn't work right the first try, and I corrected them to produce this script. So I don't want to create the impression that our programmers just always know what the next line should look like. Sometimes we have to figure it out and retype the variable names to see just what's stored there as we go, and we figure it out. So if writing R does not come naturally to you, that doesn't mean you're not a programmer. It means you're a human being. All right. So with that said, I'll go ahead and shut this down, and I will look forward to seeing you tomorrow morning at 9 when we have a lecture, if I recall correctly, about databases and repositories. See you then.